everyone, back to my channel. Today I'm here with another interesting problem in physics, and this problem has a very special solution which applies Snell's law not to light but to sound. So here we can see the problem on our screen. AB is the boundary that divides two media 1 and 2, having bulk modulus in the ratio 3 is to 4 and density in the ratio 4 is to 3. Speed of sound in medium 1 is this. Source is stationary and observer can move with a maximum speed of 15 meters per second. Frequency of sound produced by source is f naught. Assume that sound waves allow also to follow Fermat's principle of least time. Do have some options for this problem that I'll be sharing in the later half of this video. First, we'll examine this problem, draw the diagram, and see how to proceed with it.
So here, as everyone can see, this is the diagrammatic representation of the problem. This is the source as mentioned in problem. This is the observer. This is the boundary separating the two media, medium 1, medium 2. The distances have been given in the form of the variable L, where L can be assigned any value. This is 4 times L, this is 3L, this is 7L. So let's see what happens here. Source emits sound which will travel like this in every direction. We can assume spherical wavefronts which will go out from here, touch this media and change speed, because the speed in these two medias are not same, as their bulk modulus and densities are not same. So the sound will travel from here, go here, and will not go in the straight line but will follow some other part so as to follow the Fermat's least theorem principle. We will discuss that later, but first we should find the speed of sound in medium 1 and in medium 2. The speed of sound in medium 1 is given itself in the problem to be equal to 300 meter per second. So let's write that. Velocity of sound in medium 1 is 300 meters per second. We can now use the Newton's formula for velocity of sound in a medium, that is equals to under root bulk modulus divided by density. This is the Newton's formula with Laplace correction. So we have bulk modulus of medium 1 upon medium 2 is given to be 3:4, and density of medium 1 is to density of medium 2 is given as 4:3. So velocity of sound in medium 1 is to velocity of sound in medium 2 will be equal to under root bulk modulus of 1 upon bulk modulus of 2 into density of 2 into density of 1, which is equals to under root 3 by 4 into 3 by 4, which is 3 by 4, which velocity of sound in medium 1 is 300 meter per second, which is 300 over velocity of sound in medium 2. So velocity of sound in medium 2 is 400 meters per second. Now we have the velocity of sound in second medium and velocity of sound in medium 1. Now we can apply Fermat's theorem of least time to this problem and find how the sound will deflect. But before doing that, we should discuss what does Fermat-Little's theorem state and how does it work with light and how this transformation will work in this problem. So Fermat's theorem states that whenever light from one medium travels to another medium, it takes the path which takes light ultimately least time to follow. We can say that, say the speed of light in this medium is c, and in this medium is c by mu, where mu is the refractive index of this medium. Then the path that light follows such that least time is taken by light to go from point A to point B. Let's say this angle is I and this angle is R. Then we can mathematically express this information by Snell's law, which states that sine I is equals to mu sine R, where mu is the refractive index of this medium and the refractive index of this medium is assumed to be 1. So 1 into sine I is equals to mu sine R. This is the mathematical representation of Fermat's least time theorem. So let's apply this to our problem and see how this will work in that problem concerning sound. We can apply the Fermat's theorem in this problem because sound and light can be treated analogous in this condition, not in every condition, because light is an electromagnetic wave and sound is a mechanical wave. But in this problem, there is nothing concerning their characteristic, but this problem is solely based upon the nature of EM wave. Hence we can treat sound analogous to light and use Snell's law as we use in light. So let me draw a diagram and show you how will we do that. So this is how this will happen. The sound from the source will travel along the straight line, and when it meets this boundary it will shift towards the normal because this medium is denser than this medium. Denser means this medium has a speed of sound less than this medium. This is analogous to optical density, in which we say that a medium is optically denser than another medium when the speed of light in that medium is slower than that in another medium. In medium 1 speed of sound is 300 and in medium 2 speed of sound is 400. Hence medium 1 is denser than medium 2 in terms of speed of sound. So this is how we will do this. This is this is I and this is R. Let us assume the refractive index in terms of sound of this medium be mu1 and in terms of sound for this medium be mu2. Let's apply Snell's equation and see what will happen. So mu1 sine I must be equal to mu2 sine R. Now let's see what mu represents. Mu represents how fast or how slow does light travel in a medium. That is, C always represents, mu always represents C, speed of light in vacuum, upon V, where V is the speed of sound, speed of light in that medium. For sound, we will treat C as a universal constant, that is speed of sound in general, and V as the speed of sound in that medium. Let's now use this definition over here. So mu1 can be represented as C, speed of sound in medium 2 is 400, C over 400 sine of I is equals to C over 300 sine of R. This C cancels this C, 4 cancels this. So sine I must be equal to 4 by 3 sine R. Now we have a relation between the angle I and R, but this is not enough to solve this. So let's now apply geometry and some trigonometry to solve these angles I and R. Let's assume this distance to be x. So this distance from this point till this point will be 7L minus x. And in this triangle, this is angle R. So this must be R because these two lines are parallel. This is R, this is X, this is 4L. Now we can derive the expression for sine I and sine R. So sine I can be written as perpendicular upon hypotenuse. Perpendicular is 7L minus 3, 7L minus X divided by under root 7L minus X whole square plus 3L whole square, and sine R can be written as perpendicular upon hypotenuse. Perpendicular is x over under root 4l whole square plus x whole square. Now substitute these into this. So sin I can be represented as 7l minus x over under root 9l square plus 7 times l minus x whole square is equals to 4 by 3 times sine of r x upon 4l whole square plus x square. Now we need to solve this to find the value of x. I'll leave the solving this to you, as I have already taken out the answer for x. We will directly use this value and see what will happen next. After solving this equation, we arrive to the conclusion that x is equals to 3l. Now let's see what does this mean. X is equals to 3l means that this distance is 3l, this is 3l, this is 7l minus x, which will be equal to 4l. So this angle sine of I can be represented as perpendicular upon 3l whole square plus 4l whole square. This is a Pythagorean triplet which gives us 5l whole square, 4l over 5l. This. So sin I comes to be 4 over 5. This is a standard result for which I is equals to 53 degrees. This is 53 degrees, and for this is equals to 3l. This is also a standard result. This will be 37 degrees. So what does this mean? This means that the observer will not observe the source to be at 53 degree from this, but he will observe it to be at an angle of 37 degree. That is, he will observe the apparent position of this source, not the real position. He will think that the sound is coming from here. Now we will stretch this ray and we will get the apparent position of this source. Now let's see what other options do we have in this question and how can we calculate those options. So these are the two follow-up questions that the original question asks us. At what angle should the observer walk to observe the maximum frequency of the source, and what is the maximum frequency that the observer can observe? So let's first discuss why are we concerned with the maximum frequency and why do we have a case for maximum frequency, that is, why does frequency change? So the frequency changes because of Doppler effect. Doppler effect is the apparent shift in frequency heard by an observer due to the relative motion of observer and source, which over here is quite complicated, so we will use the diagram and the angles found to get to the answer to these questions. So this is the case. The observer, this is the source, these are the angles. We know that observer can move with a maximum velocity of 50 meters per second. But where should the observer move to observe the maximum frequency? We can do one approximation over here which will make this problem super easy. What we can do is take this source and keep it over here, because this observer will not observe this source over here, but it will observe this source over here, that is in this straight line. Just as in light, whenever refraction happens, the refracted light ray observed by the observer is found by stretching this refracted light ray. So in the same way we can stretch this sound ray backward direction and trace the source. For simplifying this, we can treat the source to be over here at S dash and neglect this source. Now let's see how to apply Doppler's formula and find the maximum frequency and where should the observer walk. So in Doppler's formula, we know that V F apparent is equals to F naught velocity of sound minus velocity of observer over velocity of sound minus velocity of source. This is Doppler's formula. So we need to find the maximum frequency as heard by the observer. For this, the observer should move in the straight line connecting the observer to the source, that is in this line. This is horizontal, so this must be the angle. This is equals to 37 degree. Therefore, the observer should move at an angle of theta equal to 37 degree from horizontal to observe the maximum frequency. Now let's calculate the maximum frequency which can be heard by the observer. So F apparent is equals to F naught velocity of sound. Source emits sound in this direction. So this is the direction of emitted sound. Let's take this to be positive and this to be negative. So velocity of sound in medium 1. Minus velocity of observer. The observer is moving towards this direction which is negative, so minus of V naught upon velocity of sound minus velocity of source, which is 0 in this case. So F apparent is equals to F naught velocity of sound in medium 1 plus velocity V naught upon velocity of sound in medium 1. So F naught into velocity of sound in medium 1 was 300 plus V naught was 50 divided by 300, which is F naught 350 over 300, 7 over 6. So F apparent is 7 F naught over 6. So this is the maximum frequency which is heard by the observer when he or she moves at an angle of 37 degree from horizontal. We can also trace the apparent position of the source, which will be in this direction, that is by stretching this refracted ray. So we have finally solved this problem. It was quite an interesting problem which uses the concepts of light, and we need to make those concepts analogous to sound so as to solve this problem. Interesting problem. So thank you all for watching this, and I'll be back with more questions like this.